I think we're about there. Welcome back, everyone. Well, looks like it's going to be a small class, but we'll still definitely get through it. Thanks for making it, folks who made it today. We have a pretty even set, 2 representatives in Zoom and 2 representatives in class, so should work out smoothly. Our goal today is just to, well, we didn't really get too far on chapter 19. We mostly discussed the definitions. So we're going to get through major parts of the categorical data analysis by looking into confidence intervals first. Then if we have time, we'll look into some of the hypothesis testing, but we'll probably definitely be finishing this chapter 19 when we return on Tuesday's class next week. Well, any questions at all, folks, to start us out today? Okay, let's get to it then. So as far as chapter 19 goes, there's a definite analogy with what we're doing. Think of chapter 19 as being very similar to chapter 17. Chapter 17, we're handling just one mean, but this was quantitative data. Then chapter 17 looked into the difference between 2 means. This was one quantitative variable, as well as a categorical variable. The categorical variable is categorizing which population did the individual or which sample did the individual come from. So now in chapter 19, this is like chapter 17, one proportion, and chapter 20 is going to be like chapter 18. We'll look at the difference between 2 proportions. After that, we'll look into some chi-squared methods where we don't worry about this part, the categorical variable having exactly 2 categories. We can extend this, but if we have more than 2 categories we're looking into, that would be the chi-squared procedures. So after chapter 20. So here's where we're at so far, folks. We're looking into a brand new variable. The variable for P is now going to be a parameter since it'll denote the population proportion of successes. So in order to get a good estimate on the parameter P, this is the unknown, we calculate something from the sample, P hat. That's what makes this the statistic down below. What we do is measure the number of successes in the sample, divide by the sample size, and then we'll call that the sample proportion of successes. So to test our knowledge on this kind of definition, really the best way to absorb this is to run it through an example. And that's what example 1's role is. Really short problem, not a lot of context, pretty silly as well. And first thing we want to discuss is, what is the unknown parameter here? Unknown parameter is referring to P once again, which makes this problem really confusing when you look at it. It says, the article, Facebook Etiquette at Work, published in 2010 in USA Today, reports 56% of people participating in a survey of social network users said it was not okay for someone to friend his or her boss. So they gave us a percentage that honestly feels like a parameter, but we have to know when it said 56% of the people participating in a survey, they're talking about the sample now. That means this 56% is the statistic, not the actual parameter on this one. Kind of unfortunate. But just like any good statistical problem, we wouldn't be doing a further analysis on this if we knew the exact value of the parameter. We would just tell you so. There's no reason to do further testing. So what this article has done is attempt to estimate the unknown parameter by calculating a statistic. And notice we're only being given the statistic. We don't even have the margin of error on that thing. Nonetheless, we can describe the unknown parameter. We can say that this is P. Already out of the gate, that might be a bit confusing, right? Every time we said describe the unknown parameter, we were going for mu. But there is no mu on this one. The data is categorical. So we use P instead. If it was quantitative, that's not going to fit in there even if I try to cram it. Let me try to put a better comment over here. I guess we did say it. If it was quantitative data, I should have looked at my own writing up here. We would have used mu instead. But for categorical data, we use P. So generically, what is P? It's the true population proportion, P, of successes. So we could come down here and say P equals the true population proportion of, and then beyond the of, at this point, we must say what a success is. Which is vague because we've been saying all along, this is categorical data, even in example 1, with exactly 2 outcomes. The outcome that seems to be the main interest of the study in question, we denote by a success. And the other outcome will be a failure. Looking at the study, it says users said it was not okay for someone to friend his or her boss. That's the only thing we know about the survey. That must be the success, saying it's not okay. A failure would be saying it is okay to friend your boss on social media. So we take what we consider to be a success, that statement there, and we have to write it into the problem. If we were describing mu, we would say it's the population mean of, and we'd have to say, what thing are we actually estimating? Is it time, distance, something like that? But here the analogous thing is we say what the success is. So a success here will be P is the true population proportion of people who say it is, the success in this study is saying not okay. So we'll say not okay to friend their boss. So that's the first part. We're now saying P is a percentage or a proportion, if you prefer to think of it as a decimal number, of people who say it's not okay to friend his or to friend their boss. Let me indicate a success this way. It went that far all the way to that spot. But we also have to say what the population is. That's exactly what we did for mu. We'd said whenever we describe mu, it's the population mean of something, maybe pH, that's the unit, and mirroring what a success is. But we also said what the population is when we described mu. Maybe we said mu is the true average pH for all high mountain lakes in the Southern Alps from that last exam problem. Same issue here. Once we get the success down, next thing you need to write in is the actual population. But the population is not too bad here. We just look, where did the 56% come from? It was of people participating in a survey of social network users. Looks like this right here, social network users, seems to be describing the population. We're interested in all social network users and the percentage or proportion of them who say it's okay to friend their boss. So this part is the population. And we have to write it into our description of the parameter as well. So true proportion of people who say it's not okay to friend their boss among all social network users. And at that point, we've got it, folks. That's describing the full unknown parameter, P. When you think about it, it's not as bad as it seems. We just have to know what's expected, what parts are need to be there. When we looked at 56%, that's the statistic. And it said 56% of people participating in a survey of social network users, that's what we said here, among all social network users, said it was not okay to friend for someone to friend his or her boss. We said that here. People who say it's not okay to friend his or her boss, I keep tripping over the word there. All we're really doing is taking this line and just recalibrating it so it's talking about everybody, the entire population, not just the people participating in the survey. So that's how writing down a parameter goes each and every time, but it just definitely feels different once you change the nature of the parameter because we're dealing with categorical data. So this is a good one to spend a lot of time on because every single conclusion with categorical data is going to depend on what you wrote down right here, what the parameter was. Any questions at all, folks? Nailing down the parameter for this one. Okay, Next part is a little bit easier. It says, state the value of the statistic. And there it is, automatically a statistic because it said 56% of people participating in a survey. Let me try and get that word survey in there. So that further description highlighting green made it a statistic. We're only looking into the sample of the 1,000 Facebook users. So all we need to write down here is, good idea to put down p hat, because that's us reminding ourselves we're talking about the actual statistic at this point. So p hat equals 0.56. And notice I did make a big change. We had this in percentage form. I definitely would accept it for full credit if you wrote it as a percent down here. It's just a unit change, really. But it's a good idea to make that a percent because in all formulas, p hat is a decimal. And if we make a mistake in feeding a percentage into the formula, we're off by a factor of 100. So that would be a huge numerical error to make at that stage. So just a good practice to get into for this kind of problem. So that's the value of the statistic. And last question is, how many successes are there in the actual sample? Well, the sample is right here, 1,000 Facebook users. So let's just write that in. N is 1,000. We can find the number of successes because p hat is the sample proportion of successes. You just multiply p hat by 1,000 and you're done. 560 successes altogether. But let's do it in a slightly different way, because if we take this structure right up here, that's p hat itself. This is another great way to think about it. Variable x does get used here and there. So good way to remind ourselves of the role x plays is to just directly use it. So let's write in here, p hat is equal to x. X is always defined to be the number of successes in this context. See the numerator in this fraction right here. Divide by sample size n. This would then imply that if we want to know the number of successes, just solve for x in that formula. X equals n times p hat. So now with that formula nailed down, we're done with that structure there. We just grab the information we have in the problem. So sample size n is 1,000. P hat is 0.56. And thinking about it, sure, we're doing literally 0.56 times 1,000. But doing it this way is just tying together in our mind, what is p hat? How do we calculate it? We're just getting more familiar with the formula. So I guess we don't need a calculator for that. This is 560 successes. So example one is just the basic information we need to know if you're dealing with a new data type and a new parameter, which implies a new statistic all at the same time. Any questions at all, folks, running through any one of those elements? Okay, so this is just a typical study. They gave us a p hat value. P is totally unknown, but the study probably did a whole lot more. It probably did provide a confidence interval. We'd have to buy that article to know for sure, so let's skip that. Instead, let's just describe ourselves. How would we do a confidence interval if we needed to? What we really need is a central limit theorem. So on the top of the notes was the central limit theorem for means. Let's take a gander at it for a moment. The sampling distribution of a statistic, but the one for quantitative data, x bar, is approximately distributed in this way, where we take a parameter, the mean of the population, drop it there, take another parameter. So this is more complicated than what we're dealing with in these notes. It's a 2-parameter family distribution. We take the other parameter, sigma, drop it there. The fact that there was 2 parameters made this complicated and messy. That's why we had a t-distribution in the very first place. But this is a different setup. We've only defined one parameter. There will be no t-distribution. And the central limit theorem simplifies in a certain sense. Here's that certain sense. I mean, it doesn't look super simplified, But the fact it has one parameter is the major thing about this. This is now the new central limit theorem. Let me hide this for just a moment while we take a look at it. So in the central limit theorem, we're dealing with the population proportion of successes, P. But in order to calculate, or in order to deduce formulas for a confidence interval and a hypothesis test, what we really want is the sampling distribution of the statistic. This is mirroring exactly what we did in chapter 13. It turns out the statistic, p hat itself, follows this normal distribution approximately. This approximation is fantastic if we meet these benchmark, that n times p and n times 1 minus p both exceed 10. All we now do is put in the value of the parameter p here, here, and here, and that's the whole specification of the distribution. Sometimes we give these some interesting symbols as well. For the first thing, P, if we needed to refer to it, it is the center of the normal distribution, so we'll call it mu. But that feels very confusing because mu is not the parameter that we're thinking about, which is P. So if we want to clarify, we can call this mu of the statistic p hat. Reminds us we're still dealing with categorical data. This is just the center of the normal distribution for this new statistic here. It is pretty amazing just on its own. The normal distribution comes right back, even for this categorical data. Likewise, we might call the second portion here sigma of p hat. So that clarifies what the roles is of the first input and the second input. Anything different than what we've been doing all along. We're told this approximation is accurate, provide the number of expected successes and the number of expected failures are both at least 10. And that word is really important. Let me change my color coding on here. Instead of highlighting the normal distribution, let's highlight the word expected. What do we mean by expected is probably the bigger question. It's the question I would have here. What we mean by that is expected number of successes is the successes we expect for some given value of P. It's where statistics gets kind of confusing because we've been constantly saying parameters are unknown. In just the last problem, we said, describe the unknown parameter. It's not 56%. We have to describe it fully in words. It's the statistic that's 0.56. So how in this problem, if we're doing essential limit theorem, are we giving a value for P? It's kind of vague. Well, there's two ways this happens. Think in hypothesis testing. You set up a null hypothesis that P equals a value to be tested, P naught. And the number one step you take in hypothesis testing, no matter what the context, is you assume that the null hypothesis is true, literally true about the population to see just how extreme our data is. In that context, you do supply a value for P, and we do have a notion of expected successes when a null hypothesis is true. Must exceed 10 here. This is expected failures, must exceed 10 here. But there's yet another context. Sometimes we really do assume a given value of P if we're doing a so-called what-if analysis. We've looked into one of these before, so this is our second version of a so-called what-if analysis. This is a real medication, and it's a very strange drug. I've known people who have taken Chantix. Depending on the person, it might work great, or they might become fully psychotic for a little while they're getting off that medication. It's a pretty weird one. This is going to be our what-if analysis to tie in what's going on with the central limit theorem. First, we need to absorb this context. So if you're not sure what Chantix is, it's a medication prescribed for smoking cessation. That's just what pharmaceutical companies would say. It's to help you quit smoking is a better way to say it. Targets nicotine receptors in the brain, so it can really mess with your neurochemistry a lot. It says next, assume that you're part of a research team. So you're trying to bring this drug to market. You're tasked with evaluating the efficacy of Chantix, but not in the general population. You're testing this out first, doing trials. And you don't just do trials willy-nilly. They say, after a thorough power analysis, it has been determined, this is going to be for our first trial of this drug, that the required sample size should be 1,927 smokers. They might be targeting power at, say, 99%, something along those lines, who are interested in quitting smoking. So N is 1927. On one hand, we have a sample size. They haven't even done the drug trial just yet. They're wondering, is this right? Should we increase it? Should we drop it? So we're doing another analysis. These kinds of things happen a lot when we're dealing with a major pharmaceutical company. Severe amounts of extra thought and planning goes in before any decision is made, because these decisions could influence millions to billions of dollars, depending on how bad the blowback is on Chantix if this doesn't work out. So it says, before we even select the sample of 1,927 smokers, the drug maker Pfizer requires that further analysis be done on the potential outcomes of the study. Well, this is a categorical problem. The outcomes are smoking cessation works, it's a success, the person quit smoking, or it's a failure, the person did not quit smoking after taking the drug for the amount of time for whatever the course was on that drug. We're told Pfizer believes this drug will be profitable as long as the true population proportion of Chantix users who successfully quit smoking is at least 70%. They want that benchmark, and they would never tell this to the public. But internally, this is the kind of stuff that they're doing, running numbers, trying to see if their R&D program is going to be paid for by bringing this drug to market. So they're giving us a parameter, and they're giving us a want for that parameter. Better be above 70%. So this is P set to 0.70. I guess it's defined down here as well. P is the true proportion of Chantix users that will successfully quit smoking within 12 weeks. Chantix users is the population. Successfully quitting smoking is the success. And our hope of hopes is that it's 70%. So we're going to assume that. We're going to assume P equals 0.70 is true. Not because Pfizer thinks it's true, it's because that's the lower bound, where if it dropped any bit lower, we have a problem. They may not make any money on Chantix. It's just not been worth it. They could lose millions to billions of dollars, depending on how bad this is. So we'll assume that's true. That's what we're doing here. We're assuming a given value of P, even though we have no idea what it is. We haven't even selected a sample of 1927. Again, it's just a what if analysis. What can happen if that's really true and we really selected that sample size? So here's the next part of the problem. I know a lot of context, but to do an unessential limit theorem problem, it has to be a lot of context, because it's usually a what if analysis like this. Next part says, Pfizer contacts your research team, asks you to determine the probability that the sample proportion of successes is 0.68 or lower. Why in the world would they do that if we're assuming 0.70? It's because Pfizer has determined when they do this clinical trial, they have to publish the results, required by law now. Pfizer has determined that Chantix will get bad publicity, which will jeopardize the success of this drug if this outcome occurs. If it's released to the public and they are forced to publish the outcome of the clinical trial, that 68% or even lower proportion of these users after 8 weeks were only successful at quitting, that's way lower than they wanted to, and this could cause them, again, bad blowback from the media. So the odds of this happening, the probability of getting P hat at 0.68 or lower is really high. Pfizer might cancel this entire program right here and now. So let's look into this part. Referring to P hat, when we say proportion of successes in the sample, that should really be highlighted as well to make this P hat. So this part here, p hat, and we want to calculate what is the probability that Pfizer runs 1,927 people through this clinical trial of Chantix, finds the sample proportion of successes p hat is below 0.68. It did say 0.68 or lower, so if you went less than or equals to, keep in mind in probability, same exact value. Let's go with the less than or equals to, just because it just seems to match the verbiage here. So that's what we want to really calculate. If this is something like 90%, that's going to freak out Pfizer. They're going to axe the program immediately. If it's low, like 0.001%, Pfizer is going to run the numbers, look at the odds and the expected amount of money they might make given these odds, and do a really interesting kind of business computation. But they need this information first. So that's the setup of the whole problem. This is now the question. Any questions or comments before we go to compute that value there? Okay, so in this full-on what-if analysis, we don't have a value for p hat. We just have a hypothetical value that we're going to find the probability p hat hits or is below. To do this, though, we need a central limit theorem. There's no way to do this computation unless we know how p hat is distributed and tells us it's normally. And these tell us the parameters of the model specifically. So we grab all this stuff. Notice these benchmarks of expected successes, expected failures met very handedly because the sample size is so large. So we expect the central limit theorem to be highly, highly accurate on this. So using this information, this tells us p hat is distributed normally. The true mean, when we say that, we're talking about p. We're still calling it mean because it's the mean of the normal distribution, is 0.70. So this just directly copies in here. The true standard deviation of this model is going to be square root of p. Again, this is nice. It's a one parameter description. So we take 0.70, 1 minus 0.70, then divided by sample size. I forget the exact figure, 1927. So this tells us exactly how p hat is distributed. And then it finally enables us to actually compute this. I have some regrets on my organization, though. Let me see if I can fix this real quick. I think the logic flows better if we put this on top. This is the first thought, use the central limit theorem. And then the second thought is do the computation down below. Now, once we have this on paper and the central limit theorem described right here, all we're doing is going to RStudio and running through this computation. Let me put down that the syntax on this is going to be p norm. We take this value first, 0.68. So from the probability statement, just import that directly down. Next part is going to be mu p hat, which is 0.70. Then next part, sigma p hat. Forgot how to draw sigma. Give me a moment. Sigma p hat, which becomes root 0.70, 0.30, 1927. Notice I didn't even worry about putting this into the calculator. It's no harm in just putting this all in one line and getting the most accurate value out directly. So let's go and compute this way. Using RStudio in the calculator mode, I'm just going to work off the console and directly type in this syntax. P norm, 0.68, 0.70, square root of 0.70 times 0.30, division 1927, gives us this as a probability. We have 0.0277 upon rounding. And That's all Pfizer would have wanted for your research team. They're done with you at that point. Business people are kind of weird in that sense. They'll just ask for the value, they'll get the value, and then shut the door on the business meeting. Up to them on what they want to do. It's almost a 3% chance that if they gamble on this, their clinical trial will have less than 6 to 8% successfully quit smoking, which does put the company in jeopardy. They believe this is really true and they're going to stick with that figure. Then this might be concerning. They're going to have to decide how much potential money could they make off Chantix, how much potential money could they lose if this outcome with the 3% chance really happens. So the conclusion here is that there is a 3% chance, or let's say what we had more accurately, a 2.77% chance that less than 68% of the participants in the drug trial will successfully quit smoking using Chantix. But this is not the full statement. Keep in mind, this is a what-if analysis, so we made a humongous assumption. We never knew the value of P. We're assuming it's 0.70 as a worst case scenario just to see what might happen. So we should say down here, assuming that the true proportion is actually exactly 70%. So that's what we conducted. 3% chance of a bad outcome after already looking into a sort of worst case analysis. Well, that's the rundown of how to work with the essential limit theorem. Again, these problems are weird because our major goal is to take the essential limit theorem and turn it around for statistical inference. And statistical inference, we only make an assumption for P to be known. If you're doing a hypothesis test, you do it right exactly there. So we'll come back to problems that look like this one when we're actually doing hypothesis testing. But for the moment, we're going to switch gears a little bit, still use essential limit theorem, but now look into what a standard error might be. Any questions at all, folks, with the full write down of this work here? Okay, well, now it's the fun part. We're going to take the essential limit theorem indicated right here and transform it. Well, not exactly transform it, but work it into something that's going to give us back a so-called standard error. That's usually the goal in statistical inference. If you can get a standard error, everything else really is going to fall into place. We have the model right over here. And now let's just read through example 3 just to get a feel for what's going on in this new kind of problem. No longer a what-if analysis. It says we're going to gather a random sample of size n from a population with true proportion P of successes. This is establishing categorical data, exactly 2 outcomes. So we're in the right setting. Then the sampling distribution of P hat is approximately normally distributed with mean P, they're referring to mean as in the center of the normal distribution. Standard deviation, that structure right there, they're just referring to that second part. So that sentence was just referring to the essential limit theorem. But there's also a reminder, we want to estimate P. P is a total unknown, which means standard deviation of P hat is also an unknown for us. We usually use green for that. If we can get the standard error, then we'll have a good estimate for what goes right here exactly. Well, here's our trick that we used from before. Let's see, the standard deviation of P hat is unknown. However, when you do this problem and you really gather the simple random sample size n, it's going beyond the what-if analysis. We actually have the data now. So what we can say is compute P hat. This is a known value that you get directly out of the data. In fact, just for emphasis, compute P hat equals X over N is the formula that you would use. X is the number of successes in the sample, N is the sample size. And we can say next. Then, just like in the USA Today article we were looking into with the proportion of people who say it's okay to friend their boss, even though P is unknown, it's approximately equal to p hat. So we have a pretty good estimate. The statistic estimates the parameter that it's attached to. In other words, just like with mu, approximately equal to x bar. Mu is the mean of the entire population, whereas x bar was the mean of just the sample. So really, really strong parallelism here. If you make that estimate on p hat, it means if you now not want an estimate for the standard deviation of p hat, go up here, change from parameter to a p hat in just those two positions. So this now gives us standard error p hat. This is our third standard error function. First one took x bar, second one took x bar 1 minus x bar 2. This one just takes p hat. And our fourth one will take p hat 1 minus p hat 2. It's square root of. Go back up here where the parameter existed, but just overwrite with p hat. Divide by sample size n. And that's our method. This is going to give us a really strong standard, or excuse me, a really strong way to estimate p by now giving a confidence interval. And just another reminder, the reason we have to work so hard here is there is no information on the error of this estimate until we have standard error p hat. And all the standard error p hat was doing is the following. Standard error p hat is approximately equal to square root p 1 minus p divided by n, where this thing is totally unknown. So we can approximate this with a known value and work from there. Well, any questions so far, folks, with the standard error portion? Okay, with our standard error nailed down, we're ready for the full formula. Here's how it goes. You take the estimate of this population proportion P of successes. In order to estimate that, here it is. You would just use your p hat right down below over here. But to really get the margin of error in that estimate, you multiply by a critical number z star and the standard error p hat. Notice z star makes a comeback on this one, but that's just because we have a one parameter family for the distribution. There's just p there. So that's the same standard error formula we derived. Z star satisfies the same exact formula. So this is a kind of a nice process. In fact, Z star is so nice here, you can literally go back to Moodle, all the way back to chapter 14. We were just discussing the initial ideas of inference. We had a method that's pretty similar right here. Here's how you get your Z star. All of this information is still completely relevant. So we might as well just grab it, throw it back in, and just as relevant as before, you can gather your Z star out of this table if you're targeting these common levels of confidence. If you want something more esoteric, set your confidence to anything you want on this red dot and run that syntax, and it'll give you the right Z star. So that's the whole method. I think we're ready to give it a try in an actual problem next. Any questions at all first with what we have so far? Okay, so our first problem is about, I believe, vaccines, meaning this one really old data. This is the whooping cough vaccine. So we're in 1974, a good year, I guess. It says to evaluate the policy of routine vaccination of infants for whooping cough. Adverse reactions were monitored in 339 infants who received their first injection of the vaccine. They gave us a sample size here, so let's say n is 339. We're now told reactions were noted in 69 of the infants. We don't know the severity of these reactions. They could be really, really mild, fussy child to really pissed off child in an ICU. We're not too sure. We'd have to buy and read that article to get better information. We just know 69 kids had a reaction. So what does that tell us? We want to know, before we even get started describing the unknown parameter, what is a success in this problem? Because the unknown parameter is P, it's the population proportion of, and whatever the success is, it goes right here. We also have to describe the population while we're at it, but it looks like the population would be all infants at the right age to receive this vaccine. I would just probably say all infants. Well, we need to know what the actual success is. The success seems to be the thing that the study is most interested in. Anyone see what it is? Definitely kind of tricky, right? Question over here, or statement?
Uh, I'm not entirely sure, but would it, the success, to clarify, the success is the unknown parameter, correct?
It's going to be going inside here. We'll say proportion of whatever the success is. Yeah.
Would be the adverse reactions for, uh, the reactions noted in the 69 for, the total that had a reaction to it, or,
You're definitely on the right track. It's about those adverse reactions, like you were saying. And then they told us reactions were noted in 69 of the infants, and there's 339 of them. So you're absolutely on the right track. This is the success in the study. Notice it just feels weird, right? The success here is an adverse reaction to a vaccine. It doesn't sound like a nice thing. It's only a success because this is what the article is interested in, the proportion of those adverse reactions in the entire population. So whenever you read the study, anything that has like a keyword that seems to be coming up, that's another good way to think about it. Mention adverse reactions here, and then set it again relative to the sample. That's got to be what we're interested in. So we'll say a success is having a reaction to the vaccine. This then informs us that the number of successes, which we often write in as an X, is 69. So 69 successes. And now here, when we're describing the parameter, we can say population proportion of adverse reactions for, let's see, it was first injection. I'm not sure how important that is. Let's carry it in just in case. Adverse reactions for the first injection it's the whooping cough vaccine, but I'll just refer to it as this vaccine, to this vaccine in all infants, not just the 339, all of them that would be at the right age range to receive this vaccine. I'll paraphrase that just by saying all infants. So this part where we said in all infants, this is where we're mentioning the population. If we look into how we calculate or how we describe the unknown parameter for, say, quantitative data, very, very similar. Where we put in success, we just put in what the average is for the data type and mention the unit. In fact, let's see if we can see a problem just like that for comparison's sake. down below on this one, let's see if I can find it. There it is. We're looking into radioactivity for Pacific bluefin tuna on cesium-134, since that leaked out of the Fukushima reactor in that meltdown. We said it was the population mean, but we had to say mean of what? Radioactive cesium concentration, becquerels per kilogram. But then we also had to say, what's the population? All Pacific bluefin tuna nearby the coast of California, 4 months after the meltdown in 2011. We do the same thing here, but instead of a unit for quantitative data, you say what the success is, then you just indicate the population. So similar, but definitely a little bit different and something to get used to. So with that parameter down, we're mostly well on our way. Like a lot of other problems, this is usually the hardest step. Part B is just asking if the conditions are met for the confidence interval. And what are the conditions? Different than the central limit theorem. It's kind of interesting. Those conditions say our sample has to have at least 15 successes and at least 15 failures. This is inside the sample itself. And just like other problems, we briefly discuss about randomization. We carefully check here on the number of successes in the sample and the number of failures. We have to report those values. But for the third thing, this is more left for the experts. All of our data, this is going to be satisfied. This is here for the sake of completion. If you're studying, say, a really, really rare genetic disorder, disease, something like that, and the population is small, maybe only 100 people known on the entire planet to have this condition, then you cannot take a large sample at all because the population should be at least 10 times greater than the sample size. What this does for us is it makes all of the observations independent from each other and random at the same time. So this is a condition on independence. It's something you can think about, but in a lot of problems, we don't necessarily have the expertise to definitively answer it. And in our current problem, we're talking about all infants that can receive this vaccine. There's no way this exceeds 10% of all infants on the planet. This is a worldwide vaccine. So it's, again, a condition that's just baked in out of completeness. When we ask if the conditions are met, we're mainly looking into condition 2, and then wondering if they said anything about randomization. So let's grab this stuff, run through the condition checking. It's actually quite nice after doing condition checking in the prior sections. First thing I would look into is our sample even large enough? These are the two things we want to check. N times p hat is only a formula you need to use if they gave you p hat in the problem, not the number of successes. If they gave you the number of successes, you just want to check if it's bigger than that number. So let's write in the number of successes equals X equals 69, which is greater than or equal to 15. So we pass on that condition there. Then the number of failures. By formula, nice way to calculate this is just take your sample size, subtract the number of successes, because that'll give you, if you take successes and failures, the total sample size. So this will be sample size 339 minus number of successes, 69, giving us 270 failures. Remember, failures is a good outcome in this situation. It absolutely meets the benchmark of greater than or equal to 15. So we're in good shape. So with those two conditions met, we can say the sample is large enough. So that's the major thing we want to check. Just keep in mind when you do this as a homework problem, one thing that's easy to forget is we must show, oh, wrong thing. This one and this one. We must show these values. In other words, don't just say that successes and failures are both larger than 15. say what they are in the problem, so I know that you know exactly what they are, just to help with understanding on this kind of concept. Last thing to do is read through example 4 again. For any statistical problem, you pretty much want to read through these several times. Even after you form your end conclusion, read through it again just to make sure you didn't miss anything that can potentially make your conclusion not fit. But if we read through this, it says infants for whooping cough, first reactions in 339 infants. Nothing tells us that there's randomization going on here. It was published in the Lancet, which is a well-known journal, so there's a level of trust there. But this is a very small and basic abstract. It didn't give us the full write-out. So what I would say here is the conditions are met. Provided the sample was random. Just a short statement, you don't have to say too much, because just because they didn't say it was random doesn't mean the condition automatically fails. This is just an unknown for us at this point. So we've done the tough work. Just like in chapter 14, the tough work here was stating the parameter right here. Checking conditions was a pretty tough in some of the other problems. But after that, it becomes kind of a funner process. Now we're starting to compute stuff. We want first sample proportion of successes. Parts C, D, and E, and so on are just the steps you'd want to take in order to now produce that interval. So when it says this, it is a vocabulary check we have to be ready for as a concept question, say in an exam setting. We have to know that's referring to p hat. We also have to know that that's defined to be x divided by n. So this is going to be equal to the 69 successes divided by sample size, 339. And you can jam that into your calculator if you like, but to avoid making estimates on top of estimates, I'm going to just leave it in its exact form right there as it sits. So that's getting p hat. Next part is the standard error of the sample proportion of successes. So this part right here, trying to decide on a good color for this one. Let's go with, how about, I guess green again. For the standard error right here, the symbol that we use to give it a name is SE. That's a standard error of something different from before. It's the standard error of p hat itself. So it becomes an equation, square root, p hat, 1 minus p hat, divide by sample size, n again. So now, if we write this in, p hat is 69 over 339, multiplying 1 minus 69 over 339. Then all of it divided by 339. So if we leave it in a fraction form, there's a lot to the structure that does seem to make sense. Denominators of 339 appear everywhere, and if they're off, that would signify a problem. On this one, I would get an estimate on it, but if you decide to keep it in its exact form to your final step, that would work just as well. Let's get an estimate for this one right here. So back to RStudio next. I just want a number out of this so we can use this as still in calculator mode. First type in SQRT, first find the home row, SQRT. Then start typing in these things, 69, 339 times 1 minus 69, 339, division by 339. So that's this exact structure. And we get this value out. What I would probably do in this situation is let's round to maybe 4 significant figures. Just as good generic advice, a lot of times you get extra zeros on these. I wouldn't round it to 4 decimal places. Go for 4 significant figures altogether. So this is going to be 0.02187, if I carried in those digits right. Looks pretty good. So that's finally our standard error of p hat. Any questions at all, folks, with that computation so far? Okay, next thing to do is the confidence interval itself. For the confidence interval, we need a critical number, but the critical number is really no big deal in this kind of section. You could scroll up if you wanted to and just grab that 1.9600, accurate to 4 decimal places. You could compute it from scratch in RStudio if you prefer, but it's such a known and common value. I think a lot of people probably have possibly memorized this one by now. Let's just go with the stated value, 1.9600. Zero zeros are not necessary, just a way to remind myself it's highly accurate, more than it seems. So the interval itself is now by formula. There's a lot of muscle memory here. You might have been tempted to write down X bar plus or minus, but remember that's quantitative data. For categorical data like ours, we go p hat. That's the statistic this time. Add or subtract a critical number z star, and multiply it by the standard error of p hat. So this now becomes p hat itself. I left it in its exact form, 69/339. We're adding and subtracting 1.9600. Which is then multiplied by the standard error of p hat. So this figure here, if you use it, the rounded value, 0.02187. Next, we just have to compute these values. But once we do that, we've placed p in the middle. P was the unknown parameter. It's the thing that we carefully defined in part A. And so now we have a really great estimate. It's not just approximately equal to 69/339. We can give now a whole interval to estimate p. Essentially what we're doing is we're quantifying the error and making our estimate by using that. That's the margin of error, which is the value you have to add and subtract to estimate p at that level of confidence, 95%. So just back to the calculator, a couple more computations. Reading this out, we have 69/339. I want to do the lower bound first, since I've kind of indicated I want to put that first by that inequality form. Minus 1.9600 times 0.02187 gives us, this is a lower bound. This is as a proportion, but keep in mind, it's also a percentage with the unit change. So let's round this one to maybe 4 decimal places would be generically good advice, 0.1607. And then now on the upper bound, we'll switch this to a plus, and we're as high as 0.2464. So that means adverse reactions, remember, adverse reactions of any kind, like my arm hurts and that's an adverse reaction, is from about 16% to about 24.6%. So that's what our methods give us. But we want to say that as clearly as possible, so that's what part F is all about. Just like in all the other problems we've done, it's really technical when you're looking at this. And now imagine you're not the researcher, you're the reporter on Channel 8 News, something like that, and you're just trying to tell the public what you found. You're not going to use any highly technical language. You're going to make this as direct as possible. So we need to read out that verbatim using the context, and the easiest way is to return to the top of the problem. I always put this as a part A because it's helping us come to the conclusion in our very final step. We're always trying to think about what are we estimating in the very first place. Now we can say, because it was a 95% confidence interval, with 95% confidence, we refer to P next. The true, now you could say the true proportion. the population proportion, or the true percentage, or the population percentage. There's lots of freedom for stylistically writing this out in the next step. I'll go with the true percentage. The true percentage of adverse reactions to this vaccine. I forgot to say the first injection, so let's just put it in a parenthetical. First injection in all infants is between 16.07% and 24.64%. So that's our final conclusion, getting down to that step. It's a confidence interval just like any of the other ones. Really, the only thing new here is slightly different methods for computing the statistic, completing the standard error, and definitely a different way of saying what the parameter is because we're thinking successes versus failures. But after all that, we really say pretty much the same thing. If that was mu, I would just said the true mean is between whatever those figures might have been. Well, any last questions, folks, on running through our very first confidence interval with categorical data? Okay, now other concept about this is, just like in chapter 17, sometimes the conditions are just not met. Sometimes they're very, very hard to meet. If we're studying something where the value of P is really close to 0, or maybe it's really close to 1, getting your successes and failures above 15 could take a sample size that's gigantic, and that could be too costly to even do that study. So let's take a look at this again. It's called the large sample confidence interval because if the conditions are exceed 15, it means the minimal sample size to even use this is sample size 30. That's the minimum, and that would be because you've got exactly 15 successes and exactly 15 failures. Usually you're using this confidence interval with sample sizes in the hundreds. It's very cost prohibitive. So we would want to have alternatives when the conditions are not met. There's some really great alternatives. There's the so-called Fisher exact test, but requires knowledge about the binomial distribution. And we didn't do a ton of probability in this class. But I have another one that's also very common. It's called the +4 method. So when conditions fail so badly that the sample size is not large enough, this is what we use to get around that shortcoming. So like we mentioned, if P is very close to 0, 1, then the statistic P hat itself is very close to 0 and 1. If P hat is very close to 0, N right here is gigantic to get it beyond 15. If P hat is very close to 1, then that's close to 0 right here. And so this N, same sample size, also has to be gigantic to go beyond size 15. So again, sometimes we can't even afford the study to make that sample size large enough. So here comes the +4 estimator. Probably the weirdest estimator you're going to see in class. But what it does is we add 4 observations to the sample, data that never even existed in the first place. We add 2 imaginary successes and 2 imaginary failures into the sample itself. Means we're no longer doing P hat. That one is referred to as P tilde. And tilde is shift the button to the left of number 1 on your keyboard right here. So that's where tilde comes into play. So this is read as P tilde. Weird word when you think about it and say it too many times in your head. So we added 2 successes, that's the +2. Because we also added 2 failures, the sample size in the denominator has gone up to +4. We have to really think about, what does this do for us if we're about to use this estimator? Because it seems just so very, very weird. let's jump through the conditions for the moment and look down here. When the conditions are satisfied, well, let's actually look at the conditions. There's not much to say. You have to have random data. The confidence cannot be below 90%, but the sample size has to be 10 or higher. That is very, very forgiving as far as the samples go. But just know if you do use this problem with sample size at 10, your confidence interval is going to be really, really wide. So that's the other trade-off on all this. So condition 3, same as before, we can't have a sample so big that exceeds 10% of the population size. But to think about what p tilde is doing, it's a good idea to look into what's going on right here. So the old interval looked like this. So the large sample confidence interval has form p hat, add or subtract z star, times standard error of p hat, where standard error, p hat is square root, p hat, 1 minus p hat, divide by n. But we made a pretty big change when we went to p tilde. So let's see what's really going on here. What's essentially happening is all about the numerator, p hat times 1 minus p hat. Let y equal p hat 1 minus p hat. We're thinking of this as a mathematical function now, where p hat is playing the role of, say, a variable x. It's a polynomial, it's a quadratic one, opening downwards. Let's get a good view on this. And really investigate that function. So y equals p, 1 minus p. I can't put in a p hat. So imagine that's a p hat, or can I? No, I think it messes it up. So think of that p there as a literal p hat. And recall it is a proportion or a probability, you could even say. So it is between 0 and 1. 0 less or equals to p, less or equals to 1. And we have a hack here. Let's make sure that really is a p hat. There you go, it's p hat now. So that's our fix. And we really zoom in on that. This is what it looks like. Notice in the standard error, the part highlighted in yellow, there's in fact an optimal value. The absolute maximum of p hat times 1 minus p hat is 0.25. And it occurs when p hat itself is 0.5. It's kind of interesting in a way. Let's take some old data. P hat equals 69,339, just our last problem. And let's see what happens. Oh, geez, what I do. Maybe let's call this not p hat. Let's just let it be a number. Okay, it's p hat again. So this was our last problem we were just looking into, the whooping cough data. P hat is at 0.2035. So we're about here, 0.2035. Roughly in that location. I don't think I could get any closer. So what happens when we make it p tilde? Let me see if I can screenshot that value. So now when it's p tilde, what we do next is we go add 2 successes. Now 71 in the numerator, add 2 failures. Now 339 plus 4, because we added 4 imaginary values to the sample, the value is 2.206. It definitely increases. We were at 2.203, now 0.206. Sure, not a huge change, but it was a large sample. We didn't need the +4 estimator in this problem anyways. But what's the effect of that change? It took a value that was at 0.206 and it moved it up and to the right. If you add 2 values like that, what you're doing is you're getting closer to a 0.5. which means you're getting closer to the global maximum of this entire structure right here, 0.25 itself. So now that's at 0.206. Let's see if I can get close to that. 0.20, that looks like it's one I can't quite get. I'll leave it there, 0.21, rounded from 0.20699. And on that, we have an output, 0.1659, slightly bigger than this one, but I'm noticing I was right at 0.206 for this. So let me try one more time. We hit 0.203, right about here. That's close, 0.16238. Now go up to 0.206. That's really hard to hit. Well, somewhere out here, that's pretty close. It goes to a higher value, 0.16298. But really the idea is the +4 estimator, its whole entire job is to make that part bigger. And what's the effect? If you make your standard error bigger, you're making the margin of error bigger. So let's start connecting the dots on this. P tilde makes the standard error larger. So that's the first thought to think. But then if the standard error gets larger, we're over here. And then we can say for idea 2, P tilde makes the margin of error wider. And that's a good thing. We want a conservative estimate on our margin of error, meaning we want it wide enough so that when we say with 95% confidence something happens, we're not lying. And making P tilde wider because we didn't make the conditions covers that. It makes it wide enough so our statement on confidence is accurate. In fact, this is a conservative widening. It widens it even a little bit more than is necessary, but that means when we say with 95% confidence, P is between two values, we are really giving an honest estimate there. We're erroring on the side of being just a little bit wider for safety, in other words. So that's the whole effect of P tilde. It's a weird thing. Again, we add 2 successes to the numerator, 4 to the denominator. We have a whole new estimate right here. And we'll run this through when we come back on Tuesday's class next time. I don't think we can do it in 2 minutes. But it's interesting to see how it works before we just throw this method at the wall. We're going to work it in this problem down below. And the reason we need this problem is it's already a large sample, 143 individuals, but the condition is rare, a ceramic total hip replacement where the hip itself started squeaking. They only have 10 of them in the sample. That's not enough for the large sample confidence interval. So if we use the large sample confidence interval and we go to say with 95% confidence, it's probably a lie. It's probably more like 92% confidence. But if we make our interval wider, we're now being more fully honest. That's the whole idea for using the +4 estimate. Widen out the interval, get a more honest estimate altogether. Well, we'll apply that logic of this P tilde estimator to example 5, run through some hypothesis testing down below, and then now round out this section when we're back on next Tuesday. Any last questions or comments, folks, with the discussion here? Okay, well, have a great weekend, folks. An excellent afternoon. When we come back, we'll finish off chapter 19 on Tuesday, and probably a week away from today, we'll be working through chapter 20 as well. Have a great one, folks. I'll see you all next time. Thanks, you too.
And have an excellent weekend.
Thanks, you as well. I hope you all don't have to work too hard. I think I've mostly just burned up my spring break on getting caught up with homeworks. Great.